Section 1. Here's something that will probably surprise you. A robot keeps bumping into the same chair leg over and over. You give it a more powerful AI model, still bumps into the chair. You tune the vision system, still bumps into the chair. Then someone adds a tiny piece of persistent spatial memory, and suddenly, the robot never bumps into that chair leg again. That's not a hypothetical. That's what RobotMem actually demonstrated. So, what does RobotMem actually do? At its core, it gives a robot a persistent, episodic memory of the physical world. Not just a map, that's different, but a record of specific failure events tied to specific locations. Think of it like a scar map. Every time the robot fails at something, it drops an object, it misjudges a distance, it collides with something. That failure gets logged with a spatial tag. Where it happened, what the robot was trying to do, and what went wrong. The next time the robot approaches that same area, it queries this memory before acting. It doesn't just rely on what it currently sees. It also asks, have I failed here before? And if yes, what happened? And how should I adjust? In the demos on the GitHub repo, you can see this playing out in warehouse-style environments. A robotic arm misplaces an item in a cluttered shelf zone. That failure is stored. On the next pass through that zone, the robot slows down, adjusts its grip strategy, and succeeds. Without the memory layer running the same task repeatedly, it fails in the same spot at roughly the same rate every time. With memory, failures in logged zones drop significantly after just a few repetitions. The implementation is actually relatively lightweight. It's not a massive neural network retraining pipeline. It's essentially a structured log, spatial coordinates, task context, failure type, combined with a retrieval mechanism that gets called before task execution in flagged zones. You can think of it as giving the robot the equivalent of sticky notes plastered to specific corners of its workspace. Hey, the lighting here fools the sensor. Hey, this shelf vibrates when you grab from it. The robot reads the notes before acting. Section 2. Now, let's be honest about what this system does not do, because there are some important boundaries here. First, RobotMem does not give the robot general intelligence or the ability to reason about why something failed. It records that a failure happened at a location and retrieves that record. The robot doesn't actually understand the root cause. If the reason a failure keeps happening changes, say, someone moves the problematic object, the memory can actually work against the robot. It might overcaution in a zone that's no longer dangerous, because the memory hasn't been updated or invalidated. Second, this is not a replacement for a good real-time perception system. If the robot can't see something right now, spatial memory doesn't fix that. Memory helps you adapt over time, but it won't save you from a box someone dropped in an aisle 5 minutes ago. Third, the memory doesn't generalize across environments. A robot trained with memories in Warehouse A doesn't carry useful failure knowledge into Warehouse B. The spatial coordinates are environment specific. So if you're thinking this is a transferable skill, it's not, at least not in the current form. Fourth, and this is subtle, the system can accumulate stale or misleading memories. If failures cluster in a zone early on due to a temporary condition, bad lighting during the morning shift, for example, that zone gets flagged, and the robot stays cautious there even after the condition is resolved. There's no built-in mechanism for memory decay or confidence scoring in the base implementation. That's a real limitation if you're thinking about deploying this in dynamic environments. And finally, the system has only been validated in relatively controlled, structured settings. Real industrial floors are messier, more dynamic, and more unpredictable. The gap between a tidy demo and a real deployment is always worth acknowledging. Section 3. So, where could this realistically go from here? Let's stay grounded, no science fiction. The most obvious near-term extension is adding memory decay and confidence weighting. A failure memory should probably lose relevance over time or after successful passes through the same zone. This would make the memory layer adaptive rather than purely accumulative, which would significantly reduce the stale memory problem I just described. Another realistic extension: cross-robot memory sharing within the same environment. If you have 5 robots operating in the same warehouse, why should each one individually learn that the east shelf vibrates? A shared spatial memory layer, essentially a collective failure log for the environment, would compress the learning curve dramatically. The infrastructure for this isn't particularly exotic. It's essentially a shared database with access controls. There's also an interesting angle around maintenance and facility management. A well-logged failure map is actually useful information for the humans running the facility, not just the robots. If the memory layer keeps flagging the same zone repeatedly over weeks, that's a signal that something physical needs to be fixed. A wobbly shelf, a lighting issue, a floor surface problem. The robot's memory becomes a diagnostic tool for the environment itself. Longer term, combining spatial episodic memory with lightweight causal reasoning, not full LLM style reasoning, but simple rule inference, could let robots not just remember that something failed, but build simple heuristics about why. That's still engineering, not magic, and it's a plausible research direction. If you're deploying something like this at scale and want reliable, low latency infrastructure to run the memory retrieval service, DigitalOcean's managed databases and droplets are actually a clean fit for this kind of lightweight, persistent backend, worth looking at if you're prototyping. Section 4. So why does RobotMem exist? What problem is it actually solving? Here's the insight that makes this project interesting, and it connects to a broader pattern in AI deployment that most people miss. The assumption when a robot keeps making the same mistake is usually the model isn't smart enough. So you upgrade the model, you throw more compute at it, you retune the vision pipeline, and it still makes the same mistake. But the actual bottleneck in many of these cases isn't reasoning capacity. It's the absence of episodic memory about the physical world. The model might be perfectly capable of handling a situation correctly if it knew about the history of that situation. It just doesn't know, because each task execution starts from scratch. The robot is, in a very real sense, experiencing the same location for the first time, every single time. Humans don't operate this way. A warehouse worker who slips near a certain floor drain doesn't need to re-reason every time they walk past it. They just remember, that spot is slippery. Slow down. That's not intelligence. That's episodic memory doing its job. RobotMem is essentially the engineering recognition that for physical AI agents, memory and reasoning are not the same capability, and that more reasoning doesn't compensate for missing memory. It's a surprisingly simple insight with a surprisingly practical payoff. And that's the pattern we keep seeing on this channel. The bottleneck in real world AI deployment is rarely what you think it is when you're in the lab. It's usually something more mundane, more infrastructural, and often more fixable. RobotMem is a good example of someone finding that bottleneck and building the minimal thing needed to address it. That's the kind of engineering story worth paying attention to,